cool.
Right, and then oh, it turned off when it was.
I think we did this one too, right? Or maybe not.
I don't remember doing this one. Does it change the order of them? Like if you already like started and then you go back?
No. I mean, it'll give you a different value for the number here. Like, well, I guess actually not.
It didn't though, because it went back to like the first one.
Mm-hmm.
Okay. Um, is that the only explanation that they give? Like proteins can be fingerprinted?
Yeah, they mentioned something else there though that we kind of talked about when we read that part.
This last.
Yeah.
I don't Mass to
So just because the fingerprinting is mentioned here in the last sentence, and what do they say here?
where? The proteolytic cleavage
Mm-hmm.
before analysis.
Mm-hmm. Mm-hmm.
Hmm.
So remember when we talked about like a certain reaction that makes something that involves water, and then a certain reaction that breaks something which
Right.
also involves water.
Yeah, I remember. So we were talking about like hydrolysis and
Yep.
I just like how can you tell with this sentence like proteolytic cleavage before?
So
So I remember like
Mhm.
ionization was like removing electrons. So
So
the
remember.
proteolytic cleavage was removing protons or like cleaving the protons, right?
Oh, so when we talked about it, I think
Oh, proteins.
yeah, yeah. Um, so yeah, this proteo part is referencing proteins. The
Mhm.
lysis part or lytic part is
It's
the
like
breaking of bonds, right? So you could also have like a nuclease, which would break apart nucleic acids. So proteolysis is the breaking down of proteins.
mhm.
So when we were reading this for the first time, remember how I talked about like buzzwords? So when we went and read this last sentence here, I was asking about like, yeah, what's significance of proteolytic cleavage?
Mhm.
Hmm?
Uh, Like what is the significance? Is it like what we just mentioned that like it cleaves
Protons?
proteins? I keep doing.
Yep, yep.
So if it's breaking something apart, then it's like, well, it doesn't have to do with like oxidation. It doesn't have to do with giving it a charge.
When you say charge,
Velocity of the ions is, or no, it does because that's what this whole thing is talking about, like the free protons and ions. So is it ionization? It's not an option. Could we like define all of them? Like I know what they mean, but I feel like I'm getting confused with this question.
or you mean define each of the choices?
Yeah, the answer choices.
Got it. So, okay, there's a couple of ways to like like the Gen Chem way of defining oxidation is like, Leo, loss of electrons, oxidation, gain of electrons, reduction.
Mm-hmm.
So these are like the Gen Chem definitions, but in organic chem and biochem.
Because I know it from like a biochem perspective of like,
Yeah. There's in the PDFs folder, there's like a PDF that I have that goes over like the generalized pathway for oxidation or reduction. So like for instance, if we had like an alkane here with two CH3s. So basically if when you oxidize,
we were doing this with like a question that had to do with like, was it this? Oh, we were talking about like
Yep.
the benzoquinone to hydroquinone, like which direction would be reduction, which would be oxidation.
Mhm.
I remember that.
Yeah. So when you have oxidation, you could have one of three things happening. You can have the loss of hydrogen atoms. You can have the gain of oxygen atoms, and you can also have um, the gain of bonds to oxygen.
Mm-hmm.
So what that means is, so if I have this alkane here and I oxidize it, what I'm going to first do is I'm going to get rid of two hydrogens and form a double bond. So let's say we have this, like an alkene. And now when we oxidize this, we're going to do one of those three things. So since we already got rid of hydrogens, why not add an oxygen this time? So this could be CH3, and then this thing could be CH2, and then here we can put an OH group, which would turn it into an alcohol, right? Now, um, what type of alcohol is this? The one that I just drew.
Like an
Compared to, let's say, this or that.
oh, it's based on like the structure, right? So it's like ethyl, methyl, or I can't remember the third one.
So, uh, so it doesn't have you don't have to know like that specific name, but
Just like understand that the structure is different.
yeah. So what this is, so this one here is a primary alcohol.
Right, because it only has one.
Hmm. This is the
And
secondary one.
that's a tertiary.
Yep. So in this oxidation pathway that I'm writing, once we get to this alcohol stage, I'm just going to write it here. So like if it's tertiary compared to secondary compared to primary. So if it's tertiary, like the alcohol that you make is tertiary, you can't oxidize that any further.
Mm-hmm.
It stops at the tertiary alcohol. Um, if it's secondary, it could be oxidized into, so we already took out hydrogens, we already added an oxygen, so now why don't we just add another bond to oxygen? So now this turns into a ketone.
Mm-hmm.
And it cannot be oxidized further. And now the primary alcohol would be oxidized in the same way, but this time, since it's primary, it'll be an aldehyde. Right? So now the aldehyde can be oxidized further into, let's say, so like now, so we already added another bond to oxygen. So we could either get rid of another hydrogen to make a double bond, which we can't really do here. Or we can add another oxygen entirely. So you can get a carboxylic acid if you oxidize the aldehyde here. Um, and the carboxylic acid could actually get oxidized itself by creating
You
another bond.
oxidize it like twice if it's a primary alcohol.
Oh, wait, so you're saying
Like, do you
oxidize?
see how with the secondary one, like you did it once and then like you couldn't do anything else with it, but then with the primary one, like you could keep going, like,
Yeah. Mhm.
okay.
Yeah,
And
yeah.
like at what point can you stop? Because now you're at OH. Can you
Mhm.
are you getting rid of one more hydrogen bond or
So if we could do that, or like, so when you get rid of a hydrogen bond, like the, oh, sorry, when I say hydrogen bond, I don't mean hydrogen bond. When you get rid of hydrogens, like to go to make this over here, you're replacing it with a double bond. And for the ketone and the aldehyde, you already have that double bond, the carbonyl oxygen bound to the carbonyl carbon as a double bond. So if you got rid of a hydrogen, like, it could be a little weird with that with the extra double bond. But what can happen is this carboxylic acid can get oxidized, which we can have it add bonds to the O like the OH group to get this CO2.
can I ask like this thing like fingerprinting? Is this something that like I need to know for MCAT or this is just like passage specific?
Yeah, yeah, it's not something that you need that you're expected to know. Most of the like a lot of stuff in these passages will be like that.
Given.
We want to be aware of the stuff that the buzzwords that we're likely going to, have asked of us. So, um, yeah, but
Okay.
protein fingerprinting, whatever, that's not really something specific that you need to know.
All
But
right.
they'll always say something like proteolytic cleavage or, you know, stuff that will be related to what you know. Um, so this end product of oxidation here is CO2. And like now it kind of makes sense because in our bodies, you have like for cellular respiration, you have like some hydrocarbon, which is going to be like glucose or something like that. Um, that gets oxidized and ultimately turns into CO2,
Mhm.
the last product. When it comes to the oxidation. So this is just a generalized oxidation pathway that can help us um, with questions like, let's say when we had like this, oh yeah, it's like something like that compared to this, right? So now we can see it as the stuff that's happening here, right? Because if you oxidize an alcohol, it turns into like something with that carbonyl group in it, whether it's a ketone or an aldehyde. Um, and then going backwards from the ketone or aldehyde to make the alcohol would involve you reducing it. So this generalized pathway could have helped with that question about the benzoquinone and stuff, but that's also something that they expect you to know. So yeah, it'll also be good to know that. But yeah, from this generalized pathway, you should be able to see that, like, going from here to here is reduction, and then yeah, here to here is the oxidation.
Right. We drew out this was for the benzoquine and hydrocodone question. But like as far as this question goes, I feel like I
Mhm.
understand oxidation and reduction. Um, isomerization,
Yeah.
like I want to make sure that I have like a good definition in my head of all of them because like for hydrolysis,
Mhm.
it's like breaking it into smaller things, right? So if it says like ions is inversely proportional to their mass, like to charge? Is it like mass spectrometry or something? Like, but I feel like I'm like grasping at straws here.
So are you asking
Like, I don't know. I can't tell based off of like I guess the knowledge that I have which one it is. That's like just reading through this sentence in the passage. Like I wouldn't be able to answer this question. Like I needed to have in my head like a good definition of all the answer choices to like go into it.
mhm. Yeah, so that's, that's always good to be able to find legitimate reasons for an wrong answer choice to be wrong. So
Okay.
it's good that you're doing that. Um, but yeah, they talk about this Maldi plate thing with that electric field and the velocity of the ions and all this stuff.
Mhm.
Um, but the question that they're asking us here is just, when you do the protein printing, what reaction happens? And we know that from them telling us that it's proteolytic cleavage, we know that they're breaking bonds.
Right. Breaking.
Oxidation reduction could involve breaking bonds and making bonds, but it's not like it's breaking a bond between like two amino acids or like two sugars or like two fats or something like that.
Okay. So it's not likely the answer either of those.
Mhm.
Is it like I know we spoke about this last time, how like if the answers are pretty much like the inverse of each other, it's probably not either of them.
Uh, it's kind of like if you have two answers that are, well, it depends, I guess, on what they ask, but generally speaking, yeah, if two choices are mutually exclusive, they both can't be right and they both can't be wrong. So that could be a good answer choice. But the thing with redox is that you can never just have redox and you can never just have oxidation. Like when they give you like the reduction,
Are
like
they like mutually exclusive? Like if one is happening, then the other one's happening?
so yeah, it's gonna be the opposite of mutually exclusive because mutually exclusive means it has to be one or the other.
Right.
But redox has to be both. You can't just have like that's why like a reduction, they call it a half reaction because the redox aspect of a reaction like would have oxidation as well as reduction. So
Mhm.
you can't have oxidation without reduction and vice versa.
Okay.
Yeah. And then isomerization is just moving some atom or something like in the molecule itself, but it's not like it's gaining something or losing anything. So isomerization won't be it. But
I mean, then that matches with like with the definition that I gave for hydrolysis, right? Where it's like
mhm.
breaking it into smaller, like what is it, like a peptide?
Yeah, like you can break those. So like if you had two amino acids
Hmm.
and they bind to one another, that's going to make that peptide bond, and it's going to be done through dehydration synthesis, also known as condensation, which means that you are synthesizing, making a bond through the removal of water.
Okay. And so that's probably the answer. Like,
So what I was saying was just the dehydration synthesis part, but yeah, the opposite of that, where you're breaking the bonds, would be with the addition of water. So that's why it would be hydrolysis. Yeah.
it doesn't like give you explanation. Oh, no, it does.
Yeah, there's also like the Jack Weston Chrome extension. I would really recommend because there's much better like answers explanations, and also the format of this is really bad
Hmm.
because it's not like what it's like on the MCAT, but the Jack Weston Chrome extension will make it like what it looks like on the MCAT.
Hmm. This is a new article, right?
Mm-hmm. Let's see if you could maybe zoom out like a tiny bit.
Maybe if I like go into it, it's usually better.
Oh yeah, yeah, that's better. I wonder if this bottom part we can get rid of if you select one of these confident things. Oh, it doesn't even let you select it. So never mind. It's like you would have to choose one of the answer choices. But anyway, um,
Okay.
yeah. So yeah, so same thing over here. You'll read it out loud slowly, and I will mention, I will like interject when we see buzzwords.
Okay. Um, Photoacoustic calorimetry is a technique used to determine the bond dissociation enthalpy of solute molecules.
Okay, what's calorimetry?
Honestly, not sure.
So it's a way for us to figure out how much energy is in something, like or like how how much energy is in the bonds of something.
Mm-hmm.
So the most common one is the bomb calorimeter. It's like so you probably did like some experiment in chem where you had like a styrofoam cup or something. No?
Because
So
I remember it was so long ago.
yeah. So what this is here that I drew is a bomb calorimeter. So what happens is, so this is like a big cylinder, like filled with water, which is what the light blue, like diagonal lines are supposed to represent. And then there's a little compartment there that I made like this kind of thing in orange. So imagine you had like a candy bar and you wanted to figure out like how many calories um are in that candy bar. You could put it in that little container in that bomb calorimeter and use a charge or something to cause it to combust and release energy. And you want to choose a material for the this container that conducts heat really, really well. Because what will happen is the heat that comes from the combustion of this candy bar inside will be, will reach the walls of the container, and the walls of the container are have interface with the water, so the energy goes and starts to heat up the water, and we have this thing up here which is just a thermometer, and by measuring the change in temperature of that water we can figure out how much energy was originally in that like candy bar. So, and that's because we know the like in this we would know the mass of water that we have, the specific heat of water, because it's really this thing, right? Where Q is the heat energy, M is the mass, in this case, of the water, C is the specific heat, in this case, of water. And specific heat, think about it as like it can also kind of be called like heat capacity, but think about it as how much heat something can absorb before it goes up in temperature. And so water is known to have a very, very high specific heat. So, you know, that's just like a good like standard to use when you have something like this. Um yeah, and this just lets you figure out the energy of the thing in that container inside by measuring the change in temperature. And that's just what a calorimeter does.
I remember using it.
Yep. Well, was it like with the styrofoam cups?
Honestly, I don't remember like what we used it for. I just remember like it was always like part of like the lab manual, like turn
Yeah,
this.
yeah.
Yeah.
Yep.
Okay.
So, okay, so yeah, that's a regular calorimeter. This passage is talking about some other type. Now,
Photoacoustic.
yeah, what do you think of when you see photoacoustic?
We've been speaking about like energy, so it's probably like photoacoustic. It's like something to do with sound.
All right. So the energy part we
It
know.
does. It's like light.
Yeah. hmm
Huh.
So we know the calorimetry part is the energy part, the acoustic part is the sound part, and the photo part is the light, right?
I feel like there's a lot of factors going on.
hmm So yeah. So okay, and then they're saying that this is a technique that's used to determine the bond dissociation and enthalpy of solute molecules. So that's like the energy it takes to like break the bonds, right? Okay. Um,
Enthalpy is like a measure of heat, right? It's like
yep, it's a type of heat energy. Um, and
how
you'll
much
see,
heat it takes to like break a bond or something.
yeah, yeah. That'll be like so there's like heat of combustion or yeah, heat of combustion, heat of formation. So, you know, if we're breaking bonds, it'll involve the heat of combustion and then the opposite for making bonds. But yep, basically that. So yeah, you can continue.
PAC is based on the photoacoustic effect in which matter emits sounds after it has absorbed light. A photoacoustic calorimeter schematic is shown below. Monochromatic pulse laser beam is focused on the
Oh,
same.
so okay, so once we see that figure, we want to, try to figure out what it's trying to, or try to figure out, some stuff about it. Um, so what do you see here? Like, describe it to me.
So there's like a laser of some sort, and that's like a specific distance away that's like triple the length of the lens to the sample.
Okay. Does that remind you of anything?
Like wavelength,
Um,
or we were talking about light the other day. So
so anything about lenses?
like the electric field.
Oh, I just mean like geometric optics, like where you can have a lens that would cause the light rays that go through it to converge. They could
Uh-huh.
also cause it to diverge.
Okay. But like the specifics of that, like for this question,
Huh?
like it's just we don't know anything specific about this lens, like what it how it acts. It just
Well,
I'm so confused about like the photoacoustic part. Like is it light that's traveling or sound that's traveling?
okay, okay. So it seems like um it's kind of both, right? Because we know that light is being used and they're telling us about this thing called the photoacoustic effect, right?
Mhm.
And that means that when something absorbs light, it makes a sound, right?
So light
What was that?
emits sounds. So after the light passes through it, it like creates some sound. I understand.
Yep, yep. So, yeah.
And the sample is the microphone, or the sample is like the like sound.
So, okay, so what we can do is we can, I guess, we can kind of like take a look at this like the way that we did, but you can continue, I guess, reading because they if it's not readily apparent here, then they might
Sure.
talk about it elsewhere. But I just wanted you to see that there's a lens here, and that's going to be something that
Mhm.
will be
Okay.
relevant. But yeah.
The monochromatic pulse laser beam is focused on the sample cell using a thin lens,
What does monochromatic mean?
one color.
Yeah.
Each photon causes the cleavage of a chemical bond in the solute molecules. Because the photon energy is designed to be larger than the energy needed to break the bond, the excess energy is absorbed by the solution, causing a local temperature increase, which is okay.
So let's
This fast and local.
oh yeah. So yeah, let's think about what they're saying here, right? So yeah.
That the photon energy is larger than the energy needed to break the bond. So like the photon has like energy left over.
Mhm.
What bond is it breaking? It's the cleavage of a chemical bond in the solute molecules. Okay, sounds good.
Uh-huh.
And so then this temperature increase is what's being measured by the pack.
Yeah, because they're saying that this yeah, there's going to be a local temperature increase. Good. Continue.
This fast and localized heating process creates a sound wave that reaches the microphone, which sends the sound to an oscilloscope for recording.
All right, what are they telling us here?
So they're saying that like this temperature increase
Mhm.
creates a sound wave.
Yep.
So the light, the photon from the light goes through the lens, heats something up over here, and then that sends energy like in the form of a wave towards the microphone, and then the oscilloscope records it.
So what do they say in the passage that we've read so far that tells us like so what we're trying to do is we're trying to break bonds here, right?
Mm-hmm.
So where would we're trying to break bonds in solutes. So where would the solutes be?
It's either before the lens or within the lens, which doesn't
Any,
really
any
make.
other any other choice?
Do we know like where it is? Like it says it's in
Mhm.
like we don't know where this system is, right? Sample cell.
Mhm.
Or has this I don't know. The
What?
solutes would be
So okay, so we have a pulse laser that's shooting some light. The light hits the lens and starts to converge, and it converges where?
in the microphone.
Uh, yeah, like here, right? Maybe this is the sample. Right? Because so the microphone, oscilloscope, and stuff, they're here, but you see that the light rays they converge.
Converge. Oh, okay, I get what you're saying. So they converge
Yeah.
within the microphone, right?
So let's see. Um so okay, they're telling us here something about the laser beam being focused on the sample cell, right?
Mhm.
And I know that there's a lot of stuff that are here on the right. There's sample, there's energy meter, there's microphone, there's oscilloscope. And we know from the what we're reading in the second paragraph that um where does the microphone come in, you know? Like what happens first?
The it's heated first, so that's like where the photon causes the cleavage of the chemical bond in the solute molecule. So all of this stuff happens first, and the microphone only comes in from the heat, like after the heat is already increased.
Yep. And that also means after the solute molecules have their bonds broken, right? Right, because that's what the laser beam is trying to do.
Uh-huh.
So what we really have is a sample here. It's kind of like a cuvette or something. Do you like remember that? It's kind of like I just imagine like a little clear little container where you can put your sample. Kind of like so in this here that I drew, the bomb calorimeter here, this is where you put the sample, right?
Mhm.
So for the photoacoustic calorimeter, we have same kind of thing, right? We have a sample here where there's the thing that we're trying to figure out how much energy is in.
And that's like the thing right here, and that's where like the energy meter.
Yeah, so we see that they converge here in the center of this sample here. And we know from the passage that when the sample cell has, the laser rays, focused on it, like each photon causes the cleavage or breaking some type of chemical bond in the solute, right?
Mhm.
And we know that the solute is the thing in that sample. Um, and we know that once the photons break those chemical bonds, it'll create some type of excess energy that's absorbed by the solution, just like here. When this combusts, it'll create that energy that can be taken in by the water, which lets us figure out the energy of that thing that's combusting. So, what are you thinking?
Like, are we going like to the answer, like to the question?
Oh, no. So we just are getting started. I just wanted to ask you, like, yeah, like, what do you think about how we're kind of analyzing it right now?
I understand.
Uh-huh.
I like I understand like what you're going to, like where the sample is essentially just like the original calorimeter.
Where would that microphone be in this schematic? Oh, in the one that they give us?
Where is the microphone? Is it this like platform thing that it's standing on?
Good. Yeah.
Yeah. The
So,
scope
yep.
is attached to the microphone, which makes sense. Okay.
So it's like shooting laser at some type of solute that's in a solution, and the laser is supposed to break those bonds. And when it does that, it'll release heat in the solution of the sample, and that local temperature increase creates somehow, we don't need to really know how, but it somehow creates a sound wave.
Hmm.
And that sound wave reaches the microphone, which sends it to this oscilloscope thing to record it, right? So essentially, you're using light to break bonds apart, and heating up of the solution just means that it'll create um, like a sound wave that'll get picked up by the microphone.
Okay.
So, okay. I think you're up to here.
The amplitude of the sound signal is proportional to the amount of heat produced. The energy meter, based on the photoelectric effect, uses a detector with a work function of 3.4.
All right. Photoelectric effect is a big high yield topic. Have you covered that yet?
I don't think so. Like I said, it was like really neglecting physics.
Mhm.
So I feel like
So
topics aren't really.
yeah, so there's like three major things that happen that are relevant to the photoelectric effect, but I'm just gonna go over what the photoelectric effect is first, just for time's sake, I guess. But basically, um, basically, like, let's say we have a sheet of metal and we connect both ends to a light bulb. And we have a laser that has energy that hits the metal plate. And if that energy of the laser is, well, if the energy of the laser photons are the same as the energy for a bond to break or electrons to be excited, that means that if we go in excess of that, that we're going to have not just excited electrons, but so like, okay, so for instance, so let's say we had this kind of like atom here with two shells. Okay, so I drew like an atom here with an n is equal to 1 shell and an n is equal to 2 shell. And let's say that the energy difference between the two is 1 electron volt. Now, let's say that we shot photons with an energy of 0.99 electron volts. What would happen, if anything?
I'm not sure.
Okay. So okay, this is like quantum mechanics here, which means basically like it's called that because a quanta or a quantum is like a discrete like packet of energy that's all or nothing. So if the energy required to absorb a photon for this atom is 1 electron volt, the photon that has energy that's less than that, even though it's less by 0.01, it's still less. So that 0.99 electron volt photon will not get absorbed. So nothing will happen.
So if it's because it's one, and so just because it's less, I'm sorry, I feel like like from the second you started explaining this photoelectric effect, I'm like,
So, okay, so let's see. Long story short, I'll just go into that. The kinetic energy of an ejected electron is going to be the energy of the photon minus this Greek symbol. I forgot what it was, phi or something like that, which stands for the work function,
okay.
which in other words is essentially like the ionization energy.
So kinetic energy equals energy of photon minus ionization energy.
Yeah, and that ionization energy would be called work function. And it's kinetic energy of an electron.
Okay.
So, um, so yeah, that's what the photoelectric effect is. And they're telling us that there's a work function of 3.4 electron volts. So right away, we know that that's going to be something that they'll likely ask us because it's a super high yield thing that comes up all the time.
Okay. And so then you were explaining how like if the photon, like the energy of the photon is greater than the work function, like well that's what we were talking about over here, right?
Yeah, so here
Then
I
it
just
will.
yeah, so here I just was kind of going over like the basics of like quantum mechanics, which involve all or nothing signal, or sorry, all or nothing like in terms of the energy levels. So like something that they like to ask is if this okay, so this 0.99 electron volt photon does not meet the requirement of being 1 electron volt. So a question that they would ask is what if we shot 2 photons with energy of 0.99 electron volts? What about that?
Well, 0.99 is less than the first one.
Mm-hmm. But if we have 2 photons, wouldn't that be larger?
Would be great. But wouldn't each photon be like separate and
Yes.
have its own energy?
Yes,
So it still would.
correct. So what you'll see them try to like what you'll see them try to trick you with is they'll ask you like what can we do to make this photon get absorbed? And they'll say a choice will always be like raise the intensity. But we so what you want to be aware of is that intensity is not energy. Intensity, a good way to think about it is if it's light, intensity is the number of photons. And the number of photons corresponds with brightness.
Which makes sense from a light.
Mm-hmm. But if the photon does not have the required energy to be absorbed by an atom, it doesn't matter if you have 1 photon, 2 photons, or a trillion, none will get absorbed because in quantum mechanics, you treat each, separate.
So then to define this quantum mechanics thing, I can say like, sorry, my Apple Pencil's freaking out and it like delays everything that I type by like 20 seconds. So it's like throwing me off every
Yeah.
time.
Yeah. You probably have to like calibrate it, I think, but yeah, it could be very annoying.
I don't even know what's going on anymore. But let's say like if EV is less than I don't want to like write one because that's just for this specific so energy of system, it's not going to show up.
Wait, what do you mean? What do you mean about
Like
that?
we're saying like for this example, right? Because it's 0.99, it's not going to show up because it's less than 1. It's like what is this the unit of? Like what are we testing for? Like it won't show up for like the photon.
So yeah, so good question. So let's say we shoot a photon with 1 electron volt.
Uh-huh.
Now it's like so the photon has energy of 1 electron volt, and if the atom absorbs that photon, it absorbs the photon's energy, and it has to express that in some type of way. Like an atom can't just gain that amount of energy without it changing something on the inside. So what it does is it will take so since I wrote that 1 electron volt is a difference between the n is equal to 1 shell and the n is equal to 2 shell, that means that if this gets absorbed, it will cause an electron to get excited from the n is equal to 1 to the n is equal to 2 shell.
Okay.
So it'll look like this. So this blue photon is 1 electron volt. It's enough, so it causes this electron at n is equal to 1. It causes it to get excited and go up to that higher shell.
So if it isn't enough, okay, I understand. So if it doesn't have enough energy to excite it, then it won't go up to the second energy shell.
Correct. Yeah. Like it won't be like 0.99 is like right underneath it. Like it's all or nothing. Yeah. Now,
So if EV of photon is less than the energy of the atom, then it won't. get excited.
Yeah, in term when you say energy of the atom, yeah, the energy for like the shells, for the electrons in the shells. Um,
Mhm.
so yeah, also energy and stability are going to be inversely proportional. So things that are at high energy levels are not stable. They want to, so this electron that goes up to that excited state, it's too much for it. It's like, oh my God, this is too much. I'm stressed out or whatever. And it wants to go back to its ground state. So it does that. And when it does that, conservation of energy means that it's losing energy. So it will, when the electron goes back down to its ground state, it'll then emit a photon of that same energy.
Okay. This is making more sense now.
Yep.
I feel like the first time I heard it, I was really confused.
Yeah, yeah. Yeah. So this is the most like so when I said there was like three things, like this is the most like fundamental.
Mhm.
Um Now the other two things, so the other one thing is the photoelectric effect, but another thing that shows up even more so actually than the photoelectric effect is fluorescence.
Okay.
So for that, let's see. I'll draw like another atom, like maybe over here on the top left. So I'll just write. So this one, it's gonna have n is equal to 1, n is equal to 2, n is equal to 3.
Mm-hmm.
And let's say, yeah, the n between n is equal to 2 and n is equal to 1 is 1 electron volt. But then between n is equal to 2 and n is equal to 3, let's say it's 0.5 electron volts. So the entire thing from n is equal to 1 to n is equal to 3 will be 1.5 electron volts. So let's say that we shoot a photon with 1.5 electron volts. So that can get absorbed by the atom and excite an electron from n is equal to 1 shell.
N is equal to 2.
Oh, it'll go. So like here I wrote like the energy difference between n is equal to 2 and n is equal to 1 is 1 electron volt. Um, and then between n is equal to 2 and n is equal to 3 is 0.5. So the total between n is equal to 1 and n is equal to 3 would be 1.5 electron volts, right?
Would you just know this based off of the problem, like when given that like the energy to go from 2 to 3 is like less than from 1 to 2?
Oh, that's a good question. Yeah, I mean, you're not really expected to really know that. Like they'll give you some values that would be relevant. But
Mhm.
yeah, typically as you go up to the higher shells, the energy between the shells goes down.
Is this like the substrate thing? This might be a really stupid question, but like uh the theory is that like after the first substrate binds, it gets easier to like go.
Oh, like allosteric
Yeah.
effects like that. Um,
Like I know it's not the same thing, but I just
yeah. Yeah, so I think yeah. I think in this yeah, I guess as the n value goes up, the delta n or something could go down. Yeah, I don't know if I can relate that to like the other thing, but so basically here, if we have a photon that has enough energy to excite an electron from its first shell, which is like the ground state, to the n is equal to 3 shell,
Mhm.
if the molecule, so have you ever seen like a structure of like melanin or chlorophyll or some type of pigment or dye?
Unsure.
Okay.
Maybe.
So like yeah, if you ever look up like any pigment or dye, you'll see that it will be a molecule that has a ton of conjugation.
Okay.
And when I say conjugation, I mean like there's many names for it, right? There's resonance,
Mhm.
resonance stabilization, there's electron delocalization. Um, and I think last time we talked about if you can spread a charge over a wider area, it's more stable.
Mhm.
So what will happen with fluorescence is some dye, like it's not going to be like the atom per se. I mean, sure it will be, but um, it'll involve some dye or some molecule that'll just have a lot of conjugation, which would mean resonance stabilization. So what can happen is that the molecule that is excited at with an electron at n is equal to 3 will stabilize, causing the electron to go down, let's say to the n is equal to 2 shell, without emitting a photon. So this means that this energy is being released to the environment through that type of stabilization.
Okay.
And then what can happen is, so let's, our electron is at n is equal to 2 here. It can go back to its ground state and emit a photon, except the photon it emits is now just going to be 1 electron volt. So when you have the
That's
absorbed,
the
yep,
0.5.
what's up?
Because it lost the 0.5 at the top.
Yeah, yeah.
Whenever.
So whenever you have a energy, whenever you have a photon, oh, so if the energy of a photon that gets absorbed is larger than the energy of the photon that is emitted, that's when you'll have fluorescence. And you can also see it in passages because they'll say something like something was excited at 420 nanometers and fluoresced at like 520 nanometers, um, showing you that the energy level that of the original thing it would have a if it's high energy it'll have a low wavelength. So you'll see it written like that a lot, where they'll just tell you about the wavelength that something gets absorbed and then something that gets fluoresced. So that's like these are like the three main things that you'll have to know for light in terms of like the quantum stuff, and
Mhm.
you'll see it a lot.
Okay.
Mhm.
Sounds good.
Yep.
We left off over here, I think.
Mhm.
The energy meter based on photoelectric effect uses a detection with a work function of 3.4 eV. So we spoke about work function, what that is.
Mhm.
The energy of the photochemical reaction is the difference between the laser pulse energy and the heat detected. The bond enthalpy is determined as the ratio between delta H and the efficiency of the photochemical process. Table 1 summarizes the values of the bond association enthalpy of OH bonds in phenols, SH bonds in thiophenols, and CH bonds in alkyl benzenes, and the corresponding types of lasers used.
So so far they've given us certain like variables, right? Like we have delta H and R,
Mhm.
which is proportional, which I guess is the amount of heat produced. We have delta HU, which is the difference between the pulse energy of the laser and the heat that gets detected.
There's so much going on in this passage.
Well, sure that there is, but we can we can still throw down. So if you just think about the like if you go back up to that schematic here, so like okay, the pulsed laser that comes out is going to be this EM, right?
Yeah.
So maybe I'll say like EM here. And the delta HU, what is that going to be?
photochemical reaction,
Yep.
would that like happen in the sample and that's
Mhm.
what like comes out towards the energy meter?
Yep. Yep. So that
So
would
these
be
arrows are HU.
so over here in the sample, maybe I'll put an arrow there, but that's where you're going to have your delta HU, because that's where you have the solute, having its bonds broken.
Yeah.
And then the delta H and R, they tell us, is the amount of heat that's produced by that by this reaction that goes to the microphone to get, audio picked up.
Mhm.
And they're telling us also that delta H U is the difference between laser pulse energy.
And the heat detected.
Yep. So we can write this out, right? With delta HU is equal to EM, energy like from that laser, subtracted by that heat that is released, that excess, heat that's released to create that photoacoustic effect.
Yeah.
And yeah, so there's a lot going on, but um oh, and then on the bottom, table one just shows you the different like bond dissociation energies for particular bonds and you know the type of laser used for each type.
Yeah. Okay.
Mhm.
So I feel like the experimental feature that distinguishes the PAC technique from the classic based on thermometers is that was pack like general pack based off of like water heat, like is it
So that first example that I drew with that bomb calorimeter, that would be like an example of one that used thermometers, right?
Mhm.
So um so yeah, now they're just asking what makes the pack, the photoacoustic type, different from the
weren't they all using thermometers though because it's like a measure of heat?
um wh- uh when you say that, like tell me a little bit more.
You when you were explaining pack to me, you were saying that it was the like the object is inside of it and then they measure the like there's a thermometer attached as they're measuring the like
Oh,
the
so that's just the classic calorimetry technique, like the one that we're familiar with from like I know you might not remember it from like Gen Chem or whatever, but that's like the most basic type of calorimeter.
Mhm.
So, and that's where they base, it's based on thermometers because you're trying to measure the change in uh temperature of the water. But PAC is different, right? And PAC uses, um light and sound. And we see in figure one, like the schematic of one, and there's no thermometers there, right?
And no, but aren't they saying that but it's based off of the enthalpy of solute molecules. So
Yep.
there is some sort of like temperature system involved.
Yeah, so it's going to measure temperature in a way that's not directly measuring temperature. Like a thermometer directly measures temperature, right?
Right.
But for
Oh, so you're saying that they're going through all this because they're not measuring it with thermometer. They're like, okay, I understand.
yeah, like it makes that sound, and that's what they're using.
Okay.
Yep.
All right. Is that pack? Well, isn't it that like the specific heat, or it's just comparing it to like within the water? It doesn't matter if the specific heat is higher or lower.
Oh, you're talking about
The answer
the
choices.
bomb calorimeter.
Yeah,
So, and what were you saying about that?
that it's that it doesn't matter like if I thought it was just measuring it like in comparison that like you measure the you know the heat specific heat of water when you're going into it. That's like part of the Q equals MCAT equation.
Mhm.
So then can we use this samples with specific heat larger than water? Is that like not specifically true? Like it could be lower, like as long as like you know what the constant is, like
Yep.
you're measuring it as a scale of it. So I feel like A isn't necessarily right.
Good.
Um, it's only useful in samples in the solid phase. Are you supposed to like stay away from like absolute answers?
Yeah, I was gonna say that. Like, I mean, like, it's always case by case, but in general, if you can take the value of, if you can take a word, an extreme word, and give it like a percentage, and it's 0% or like 100% or like only, which is just one. Those are all extreme words, and extreme words are easy to disprove because you only need one counterexample. So, so yeah, D, we don't like the word only here, and yeah.
Okay. Enables the measure of fast and localized heat transfer
Mhm.
process. Well, isn't it doing that? But I feel like they're all doing that, no?
We say they all are doing that.
Like both types of pack. Oh, both types of like you said, the bomb calorimeter and this one, it's like well, this one isn't local. Weren't you just saying that it's not like such a simple like heat transfer system because it was like going through the like solute and then producing bonds which are broken and then that's the enthalpy. So I feel like this would be true for the other one, not necessarily the like pack.
Tell me more about what you said about the other one.
You were saying that like you measure the heat of the thermometer, that's like the easy way to like calculate the heat of it. The
Mhm.
localized heat transfer processes, which is like quick to measure, and then you're done with your calculation.
Yeah, so the bomb calorimeter that I'm drawing here again, the thermometer is just kind of placed in the water there.
Right.
If
So that
yeah.
so then saying that like if you read the question, it's saying like what distinguishes like the classic technique based on to thermometers is that pack and so pack wouldn't be the one that's like a quicker fast and localized heat transfer process. That would be like more used to describe the bomb calorimeter.
Oh, well, the bomb calorimeter, this thermometer here, is just like it's not like it's placed in the container or anything. It's like just placed in the water there. So it's measuring like the general temperature of the water that's in that bomb calorimeter. It's not measuring it like directly or close to it. So it would be it wouldn't be localized, this type of calorimeter.
And the other one would be?
Yeah, just because they told us, right? They just said that there's a local temperature increase, fast and localized.
Oh, so this is just like literally reading the passage.
Yeah, most of the time it'll be that. Yeah. Like I honestly don't know how a local temperature increase makes sound, but we don't need to know that.
Mm-hmm. What does that sound? Where it goes? So then like just by process of elimination, it's not C, right? Because that's okay.
Mm-hmm.
All right. The reading of the energy meter in figure 1 when an appropriate laser is used in pack to dissociate a particular chemical bond. Well, it's probably not 0
Why not?
because that would mean that like no energy is going through it, which if this like reaction is happening, there is energy that comes out. No.
So let's think about let's think about the other ones, the other choices.
This is back when we were doing. So EM is laser pulse energy. Reading of the energy meter when appropriate. Wasn't it like part of this equation that we wrote out over here? That energy of the photochemical reaction
Mhm.
in HNR is the heat detected to dissociate a particular chemical bond. Well, that's the photochemical. It's this one, right?
Well, let's think, right?
Their chemical bond.
So if the pulsed laser is, so they mentioned when an appropriate laser is being used, right?
When an appropriate laser, yes.
So so in the sample, the
Oh,
energy.
so here it's a pulse laser, and you're saying that wouldn't it be a pulse laser here too? That's just what the pack how pack works.
Wait, when you said there's a
Like when
laser where? Just
I'm
like
confused, isn't it just stating that like pack is working the way that it's supposed to with like the appropriate laser? That's the pulse laser that we're seeing in the
oh yeah. So let's take a look at table 1 for a sec. Because table 1 shows you the different types of lasers and the type of bonds they break, right?
yeah.
So yeah, can you scroll down to that? So okay. Laser A has this much energy per mole, and it's useful to break OH bonds, right?
Yeah.
Okay. Laser B has a lower enthalpy, 375, and it's to break the CH bonds, right?
Yeah.
Okay. Now let's say we use an inappropriate laser. Let's say we use laser A to break CH bonds.
It wouldn't.
So this 375 is going to be one of these things.
Mhm. But you're saying that like when you are using the appropriate laser, then dissociate a particular chemical bond.
So
So when it's like the correct laser, then there's no energy being produced because it's not like the enthalpy matches.
you're on the right track. So that's why
So
I wanted to just say, okay, what if we used an inappropriate laser? Like let's say we
it
use,
wouldn't work, right?
well,
It wouldn't be as efficient at the
so
very.
let's think about these three values here. Which one would be so EM is the, tell me what that is again.
That's just the overall like the laser pulse energy.
Good. And this delta HU?
Energy of the photochemical reaction.
Good. So for this here, this 375, would that could be one of these, right?
Hmm.
Which one do you think it would be?
The HU.
Good. So let's say 375, right?
Yes.
And if we use laser A
Is the
has,
E.
yeah, good. And we can see from here that it really has like an energy of like 463, right?
Mhm.
Kilojoules per mole.
Yeah.
So if we have like a laser that is this powerful and it only takes this much energy to break the one of the chemical bonds, like for the CH bond, that means we have an awful lot of extra energy that isn't from that localized heating process, but because it's photon or it's light energy that isn't getting absorbed, right? Like if you think of like the 375 kilojoules per mole here, that's how much you need to break that CH bond,
Hmm.
right? But if you use a laser that can break bonds that are 463 kilojoules per mole, that should mean that a lot of
There
that,
isn't that energy excess left over, right? If it's like with the appropriate laser.
uh-huh. So if we used an inappropriate laser, that means that a lot of that light isn't getting absorbed by that solution and would just go right past the sample and come up in that energy meter.
Okay. So that can like that number here. So it is D, right? Because we're saying that with the appropriate laser, there wouldn't be,
Yep.
it wouldn't go to the reader.
Yep. So that energy meter is just a way to tell, like to have like to account for everything, right? If it didn't have an energy reading of 0, it would mean that we're using a laser that's overpowered, that's kind of wasting it.
Because you must read. Okay, so it's yeah. That's what we were saying that it's like 0 for laser used to dissociate.
Yep.
Okay. These are the compounds, right? Though the phenols, thiophenols, and alkyl benzenes. I would need to know the structure of like benzenes. I can imagine have the aromatic ring, but like for phenols, phenol is like phenylalanine, or
So
that's a different.
so 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 what's alanine? Like what R group?
Should I draw it out?
You could do that, or you could tell me.
Oh, okay. So just CH2.
Like CH3.
CH2. Oh, well, this one is if it's like a carboxylic acid. So yeah, CH3.
Yeah, so it's just like a carbon, right?
Yeah.
Now phenylalanine looks like this, right? Right?
Hmm.
So this part is the alanine part.
Hmm.
This part must be,
The ring.
yeah, the phenyl part, right?
Hmm.
So phenyl, the PHEN, like is benzene, essentially. And if it ends in OL, it's an alcohol. So like phenol would just look like this, which is the R group of tyrosine.
Hmm.
But so now that you know that the phene part,
Phenols have it. So then wouldn't the answer be A, that
yep,
they all have the ring?
yep.
Okay. So I feel like I learned the amino acids and I have them memorized, but then when it comes to like the like little structure thing, like
I have a very
I need to memorize. So this is in the PDF. I really need to take a look at it. I haven't looked at it because I was dealing with like the modules yesterday, but
yeah, yeah.
after my fulling tomorrow, I'll take a look.
Yeah, I have like a video where I go over the amino acids and I go over it in a way that's very different from how people usually go over it. Um, but yeah, that would be a good like I could send you the link and
Okay,
stuff. Um,
sounds good. All right. According to the passage, the
wait,
data and
I'm just gonna use the bathroom real quick. I'll be right back.
okay, sounds good.
Yeah, back.
Okay, so it's based off of the table and it's asking like what distinguishes like laser A from laser C. So it's based off of these values. So it's I think it's the formula that we were talking about before, like the E equals
Mhm.
HV or
Yep.
variations of that one.
Hmm.
And so A, I'm not sure what that means, like what enthalpy means. So if the heat is higher, then the frequency is usually higher.
Oh, yeah. So what they're trying to tell us here is that it is essentially the energy levels of the types of lasers.
Hmm.
So, which laser would have the highest energy?
Probably the one with the highest enthalpy.
Yep, because
So
that
then,
is the measure of the heat and the bond energy of the O. Yeah. Okay. Yeah. Basically that.
so
Hmm.
the higher the frequency, the wavelengths would be more like closer together, so it wouldn't be longer, it would be shorter.
Yep.
So then C is wrong. Emit fewer photons per unit of time. Do we know that based off of like just the information that we have, like the emits fewer photons?
Uh.
Like I know this one's just wrong because
Uh-huh.
like focus is
Um. Yeah, so the number of photons is like the intensity. So this can be like intensity per unit time.
And
But
so we were saying that intensity is not related to energy.
exactly, yeah.
Okay, so
Yeah. So this is what I was kind of aiming at when I first asked you like about that 12 centimeter value, the 4 centimeter value, but yeah.
mhm. The focal length of the lens.
Yeah, do you remember this stuff?
Mm-mm. It would just be a shot in the dark me answering it. Like,
Mhm. That would always be interesting. Like what would what would you say if you had to make a total guess?
okay. So from the laser to the lens, that's like the distance that the light travels. And then after the lens, that's the visible light. So the focal length.
So you have
I
an idea. Think about that, what you said with focal length, and then think about you said something about distance.
uh-huh.
So,
It's
but
distance that the light travels, but like just the focal length of the lens.
yeah, do you remember any formula that involved focal length?
Did we go over it?
Nope.
I don't remember.
So it'll be 1 over the focal length or focal point, whatever, is equal to 1 over this O isn't, well, it's not a zero, it's an O, and it means object distance plus 1 over image distance. Yeah, and this is a thin lens equation. Comes up all the time. Oh, and it's a reciprocal sum. So you've in like let's say in a circuit, if you're adding resistors in parallel, do you remember anything about that?
That was gonna be my next thing to tell you that I don't.
So yeah, two things here. Well, okay, so a focal length we know is involved, which hints that this is going to involve the thin lens equation. But that's also when you see the lens, you want to be thinking of geometric optics.
hmm
And there must be an object, and there must be like an image here. So we can treat,
So is it
yeah,
like 1/4 plus 1/12? Like what
yeah,
is the object?
yep, good. So yeah, this is the object here. It's funny because like
Okay.
object doesn't always have to be like literally an object. But you think about,
Like in my
how
head, I would think it would be the second one because the sample would be more likely
to
or
be.
image distant. I guess does it really matter like since you're adding up the values?
Oh, so
Like
in terms of object distance and image distance, like here it's not like we have like an object for an image really, but you can think of those things as
I
being,
guess anything like after the lens would be the image, which makes
yeah,
sense.
exactly. So something before it would be like the object, right?
hmm
So, you could just plug them in to find the focal length here. But I'm going to show you two shortcuts. So one way of doing a reciprocal sum would be like here, the focal length will just be equal to the product, which is O times I, over the sum, which is O plus I.
So F is equal to OI over O plus I.
Yeah.
So then that's like 48 over 16.
Okay.
You know what's crazy is that that was going to be the answer choice that I guessed because
Yeah, yeah.
12 divided by 4 is 3.
Yeah, yeah. Yeah, no, that's good. You have good instincts. Um, yeah, so yeah, this is another way of expressing this formula. But another way is that any reciprocal sum is less than, either, I guess, I don't know what to call it, but like either value, meaning if the object distance is 12 centimeters and the image distance is 4 centimeters, a reciprocal sum of those two must be smaller than either of those values.
So is that like a shortcut, especially for this question?
Yep. So we got the shortcut here and we got a shorter cut here. So,
Cool.
because, yeah, 3 is the only one that's smaller than all of them. So, yeah. And then here's
Kinetic energy of a photoelectron produced in the energy meter in the packed device when the frequency of the incident photon that is not absorbed in the solution is F equals like there's too many uh like equations floating around in my head right now because like the kinetic energy equation was the energy of the photon minus work force, right?
yeah, work
Or
function.
like work function. Is that the one that you use? But F is from F and H are from the because you can do kinetic energy is equal to HF minus the work function.
Mhm.
Work function was 3. Okay. Work function is 3.4. H is 4.1. Do we have any of the other ones? Do we know the frequency? Or do we plug in like C over lambda, which I feel like we don't know that one either.
So so look at what they're giving us in the.
Oh, they gave it.
Yep.
Okay. I have a potentially really dumb question. When you multiply, don't you add up the like the exponents? So would they just cancel out? Would it be like 0? Or you add them because it's 15 minus
Mhm.
negative. Okay, so it's to the 30. It's like 20e to the 30th minus 3.4 EV. But it's not in the right unit. Like 20 minus 3.4 would be around 17, but I don't think it's in the right units because it's EV times second and this is in hertz.
Remember what Hertz was if you deconstruct it?
Um, 1 over, or like 1 over S.
Mhm.
So then the S comes out and you're left with 1 over EV,
Just EV.
just EV. Oh, so they're both in the.
Because you're
So
doing.
is it 17?
Yep. Good job. Yeah, they have the worst solutions ever. They're just
The
like,
alcohol
right.
most likely to go to by an SN1 mechanism in acidic conditions. So these are the alcohols that we were talking about.
Uh-huh.
I know I learned about this in biochem. This was on my midterm, not my final. So SN1 reactions. I remember SN1, SN2, but what they do, I'm unsure.
Uh-huh. Yeah. Um, so yeah, I also have like in the PDFs folder like a good PDF of like
Just to
orgo,
memorize.
but basically SN2, SN1. So SN2, it's a little weird because it's the two comes from like kinetics, rate law stuff, but the SN2 is one step that involves a backside attack by a strong nucleophile. A nucleophile is just another way of, so what I always say is like if you're using like like when it comes to acids and bases, you're going to be using the Bronsted-Lowry definition, which is when an acid is defined as something that donates a proton, a base is defined as
Mm-hmm.
something that accepts. So that's when we talk about acids and bases, but when we talk about nucleophiles and electrophiles, we're talking about the Lewis definitions. So a Lewis base is an electron pair donor. That is our nucleophile. And Lewis acid electron pair acceptor is our electrophile. And the most common nucleophile you will see on the test will be a hydroxyl group. Most common electrophile will be a carbonyl group. Because you have a dipole here with a partial positive and a partial negative, and it'll attack that.
Sorry, I'm just.
Yep, yep.
Is that this one?
Oh wait,
Oh, so specific to substitution by SN. So this is SN2 that we're talking about.
so what I just showed was just showing you the most common nucleophile and the most common
Mm-hmm.
electrophile. But SN1 and SN2, right? How they're different. SN2 is going to be a strong nucleophile just coming in, backside attack, one step, substitutes itself for the leaving group. The leaving group leaves, and you have inverted stereochemistry. But SN1 is when you have like a weak nucleophile or the electrophile has a lot of steric hindrance. And if it has a lot of steric hindrance, the nucleophile can't just go in and attack. The nucleophile will have to wait until that electrophile is alone, right? Without there being that type of steric hindrance. So that happens in two steps. The first step is a leaving group leaves. And when that happens, you're going to get a carbocation. And when it comes to carbocations, in terms of stability, it's tertiary, which is greater than secondary, greater than primary in terms of stability.
Yeah,
Because
this I remember.
yep. And this is also because you're spreading a charge out across a larger area if it's tertiary, right? So not only would a tertiary electrophile prove to be, I'm just using N minus to be a nucleophile. So like this tertiary alcohol here has so much steric hindrance here, it can't even do anything. So it waits until, let's say, this leaving group leaves, and then you have a tertiary carbocation, which can spread that charge across a larger area compared to if it was secondary or primary. So both of those reasons make it so that an SN1 reaction would happen with, like, I don't want to give it away, but something, yeah, something.
So do the acidic conditions matter for like the answer?
And not in this,
Like the acidic versus basic, or is that just like
yeah, not for this question, but that can be a thing when we kind of talk about like elimination reactions. But since we know that it's going to involve something that's either tertiary, secondary, or primary, we can eliminate two choices here that are like the same.
Я не могу, я не здесь, я не дома. Hold on. Okay, well, give me 1 second. I'll be right back.
Might have to wrap it up after this question.
Okay, yeah,
Um,
sounds good.
so
I still I'm not sure what SN1, so you were explaining that. So is it this one? Is that or no, that's before it lost the nucleophile. So then
yeah, so I was going to say there's two choices here that are like the same. Yep. That you can eliminate, right?
C and D, right? Because they both have 3.
Well, let's.
Oh, but it's not from the same point.
Yep. So yeah, for each of these, like, tell me what.
Oh, OH, A, and C, because the carbon is here that it's attached to.
Good. Those are both primary. So yeah, that's where, like you said, like if they're the same, they both can't be it. So yeah, so now it's either the secondary or the tertiary, right?
So if I lost one, then it's probably the secondary, right?
Oh, so SN1 happens when
the weak nucleophile has steric and steric hindrance. So.
Yeah, so yeah, there'll be a weak nucleophile, but the electrophile will have steric hindrance, like here. So the nucleophile can't really do what it wants to do. It has to wait until the leaving group leaves and you get the carbocation intermediate. Then the nucleophile can attack from either side, giving you a product that's racemic.
You're losing me with how do you know that it's going to be a tertiary originally? Because if it goes from primary upwards, shouldn't it?
Oh, sorry. So this is just stability of a carbocation. So for instance, we can have a secondary alcohol here that if that alcohol gets okay, so the acid here, like it's going to be like, you don't necessarily have to know this, but if you think about it, acid will donate protons. It'll donate a proton to the OH group, making it a positively charged OH2 group, aka water, aka good leaving group. So that would be gone, and then you just have this positive charge here between, the two carbons, and this is the secondary carbocation intermediate.
Mhm.
But then if you have this, which is primary, and then we protonate that, it leaves, you're just left with like one,
That's primary.
it's like two
Yeah.
carbons, but yeah.
So it would
Yeah. What's up?
be secondary. So it is secondary.
So yeah, when it comes to the type of electrophiles, it will be like this. It'll be like SN2 would be best for primary, and then secondary. SN1 would be best for tertiary, followed by secondary. So secondary is when they can both happen in an overlapping kind of way, but they usually won't really ask you about that. They will ask you like more of what you expect, with SN1 being for a tertiary electrophile and SN2 being primary.
So SN1 is primary, but didn't we just cross out those are the primaries?
Sorry, so yeah, I'll write it. So like here.
Right. Oh, so it's 1 to 3.
So 2 is, so secondary is where,
Two is like this.
what's up?
So that's kind of like the middle ground between both of them. So that's not really like
Yeah.
okay.
So they'll usually not ask you about it like that. Yeah. So yeah, it's going to be that because it's bulky, which means that a nucleophile can't just come in and attack, and it would have to lose its leaving group, becoming a carbocation, and tertiary carbocation is more stable. So yeah, you'll see more in the PDF. Yeah.
Sounds good. Okay.
Awesome. So good work today. When would you like to meet next?
So I'm gonna take the full length on Saturday. Let me just quickly go in my schedule to make sure I don't have anything Sunday. I know I have a lesson, the break class on Sunday at 2:30, but otherwise I can meet whenever. So it's 2:30 to 4:30. Oh, 2 to 4:30 I'm busy, and then otherwise I can meet whenever on Sunday. And then hopefully I'll have the full length to review with you, and then I can bring like my questions. I'm planning on flagging stuff while I take it, so that if there's like a concept that I'm not sure about.
Yeah. So yeah. So okay. Let's see. Would Wednesday work? The 22nd? At 5:30 p.m. Eastern? Okay.
Right.
So Wednesday the 22nd, 5:30 Eastern. Awesome. Good. So I'll see you then, and good luck on the test that you take. And
Yeah, and then so Sunday I'll review it. That works better probably. So
yeah, and try the blind review. I don't know if I talked to you about that, but
you did, yeah.
oh yeah. Okay, awesome. Okay. I will see you then. Good luck.
All right.
Have a good
Bye.
week. Take care.